Hello all. Today we will discuss single slit diffraction. Before proceed to discuss the details of single slit diffraction, let's first discuss the double slit interference experiment and its results. Here is the double slit interference experiment setup. In double slit interference experiment setup, we have two slits and a screen placed at a distance of d from the slits. Now these two slits are illuminated by incoming plane wavefronts, and when a single wavefront approaches the slit in the slit plane, this single wavefront is now divided into two different wavefronts, and each of them are going to act as a separate source of light as per Huygens principle. Now when this wavefront approaches the screen, they will propagate as a spherically diverging wavefront, and each of them are going to constructively and destructively overlap with each other and produce this interference pattern on the screen. Now consider the single slit diffraction setup. Here we have a single slit of width A that are illuminated by incoming plane wavefront. When a single wavefront is at the slit plane, we can consider infinity number of points, and all of them are going to act as a separate source of wave as per Huygens principle. Now when this wave propagate towards the screen, they will propagate as a spherically diverging wave, and these waves overlap with each other and produce diffraction pattern on the screen. So here the diffraction pattern is basically resulting from the interference of light that are coming from infinity number of points from the slit plane. To establish a condition for minimum, I am going to divide this slit region into two zones of equal width. The top zone is denoted as R1 and the bottom zone is denoted as R2, region 2. Here the point P0 is the point of central maximum, and P1 is the first order minimum, P2 is the second order minimum, P3 is the third order minimum. So the zone R1 has the width of A by 2, R2 has the width of A by 2. Now I am going to consider two rays from these two zones that are extended to the point P1. So from the top zone or region 1, I am going to extend a ray from the top portion of the top zone to P1. Similarly, I am going to extend another point from the bottom zone's top portion, that is from this point, and denoting these rays as R1 and R2. Now these two rays, since they are reaching to the point P1, they should destructively overlap here, and since the P1 is the point of minima, whatever rays that are coming from the slit, they should overlap at point P1 destructively. So the path difference should be lambda by 2. Path difference between ray 1 and ray 2 is lambda by 2. Now how to estimate the path difference? To find the path difference of this ray 1 and ray 2, I am going to draw a normal line from the point A2 to some point in the ray R2, which I am denoting it as P, let's say, and the ray 2 makes an angle theta with the central axis CP0. Okay, now what will be this angle then? We know when a line cut two parallel line, so if this angle is theta, this angle also must be theta, since these two are corresponding angle. Okay, now if I place the slit at infinity distance from the slit, means if I place the screen at infinity distance from the slit, I can approximate this triangle as right angle triangle and express the length CP as this portion, CP as A by 2 sin theta. Remember, this side is A by 2. Okay. Now, this is the path difference between two rays. If we consider two rays that are extending from the point A and point P, there won't be any path difference between these two rays when they reach the point P1. The entire path difference is coming due to ray 2 covers an extra distance than ray 1, and that length is exactly Cp, and that is A by 2 sin theta. Let me put that here. So A by 2 sin theta is equal to lambda by 2. So these two are getting cancelled. So A sin theta is equal to lambda. This is the condition for first order minima. Okay, in a much similar way, to find the condition for second order minima, I am going to divide the entire slit region into 4 equally spaced regions. This is my region 1, this is my region 2, this is region 3 and region 4. Okay, each of this region has the width of A by 4, A by 4, A by 4, A by 4, and the point P is the center of central maximum, and point P1 is the first order minimum on the screen. Now, from each of this region, I am going to extend one ray to the point P1. Okay, from region 1 to P1, ray 1, a ray 2 from second region to P1, and ray 3 from third region to P1, and ray 4 from the fourth region to P1. So this is my R1, R2, R3, R4. Now the angle, each of this angle makes theta with the horizontal line. This is also okay. Now this angle is theta, and this angle is theta, this angle is theta, and all of them are equal. Okay. Now this is exactly the same angle that a line drawn perpendicular to second ray. So this perpendicular line will make exactly the same angle. Since they are corresponding angle, this will be also theta. Okay, now here also it is theta. Now if we consider a point P on ray 2, and any ray that is going from A and point P, when they reach point P1, they won't have any path difference between them. The path difference arises due to R2 covers extra distance equal to dP when they reach P1 than ray 1. So the path difference between ray 1 and ray 2 is exactly dP. Similarly, the path difference between ray 2 and ray 3 is, let's call this point as S. Okay, and the path difference between R2 and R3 is CS. Similarly, the path difference between ray 3 and ray 4 is, let's call this point as T, ET. Okay, so how much is this path difference between any pair of rays from any two adjacent region? That can be estimated in terms of sine of angles of this theta. Okay, so A by 4 sine theta will be equal to this path difference, that should be lambda by 2. Since all of them are reaching to P1, P1 is the point of minima, and the path difference between these two should be lambda by 2. So the A by 4 sin theta is equal to lambda by 2 between ray 1 and ray 2, and same relation holds for R2, R3 and R3, R4 as well. So cancelling this gives a by 2 sin theta is equal to lambda, a sin theta is equal to 2 lambda. This is the condition for second order minimum. So if we in a same way we can split the entire slit region into n equally spaced interval or n equally spaced even interval, and can apply the same notion there and find the condition for nth order minima. So the generalized relation for nth order minima, condition for nth order minima is equal to n sin theta is equal to a sin theta is equal to n lambda. This is the condition for nth order minima. That's all. Thank you.